Hey, welcome back. We're going to power through the rest of these. Let's start at number 10 on page 226. And basically what this tells us that these two individuals, and we're just going to write them like this, have a carrying a recessive trait. And so if you could do the Punnett square, but if you do a Punnett square, we know that 3/4 of them will be normal. And basically, every time they have a kid, it's an individual event. So you have 3/4 chance the first child is going to be normal, 3/4 chance the second time it's going to be normal, and 3/4 chance the third time the child's going to be normal. And you're going to get 27 over, what did I get? 27 over 64. Okay, that's answer number 10. Pretty simple. And each event, each child, is an individual event. Just like flipping coins. So let's do number 11. Number 11, you have a tetrahybrid cross. And basically what you get here is you have these parents. And you're self-crossing them. Oh, goodness gracious. Now, you're not going to set up a Punnett square. That is ridiculous. So you have to use a little bit of math. And so basically, what are the chances that they're going to have if you look at the one E, what are the chances that they're going to have a kid that's this? Now, again, like I've said before, each one of these we're assuming is on a different chromosome. So it's going to do its own thing no matter what anything else does. That's independent assortment. So basically, we're going to look at this individual here crossing with this individual here, and we're going to get 1/2 chance. If you do a Punnett square for just the B's, you're going to get chances of getting a homozygous dominant is going to be 1/4. C's, 1/4, and little d is 1/4. Okay. You can do the math on this, and I think on the math on this you get 1 over 128. Okay. Now remember, each one of these is an independent event. What the A does not affect what the B does, what the C does, and what the D does. Okay. So, 13, Karen and Steve. Not the Karen and Steve in our class, a different one. What are the chances? Okay. So let's go on to 13. Karen and Steve. I like to do pedigrees on these so you can actually see their outcome and the parents and the connectedness to their siblings. And it says that they both have siblings with sickle cell. And that doesn't really matter what gender that is. And it also says that they do not have it, and their parents do not have it. So the question is, if they have a kid, what are the chances the kid will have sickle cell disease? Okay, we need to do a little bit of math here. I know the genotypes of the parents. I know each one of their parents is got to be a heterozygote. How do I know that? Well, the only way this can happen, and them not having it, and Steve and Karen not having it, is if they're carriers. So they're not showing the trait, but they're carrying the trait. So now, what are the chances that Karen and Steve have it? You do a Punnett square of the parents. Oops, a little less here, just not to confuse you. Steve, theoretically, could be big S, or he could be big S, little s. Same with Karen. Right? Because these are their parents. They can be big S, or they can be little s, big S, little s. However, the only way that actually you can possibly get an individual with sickle cell disease is if they're both carriers. So now we need to figure out, we also know that Steve and Karen are not homozygous, so we can rule that out. So let's take a look at this Punnett square again. With the parents. Big S. Little s. Big S. Little s. Little s. Little s. Now we're going to rule out this for both Steve and Karen because we know they do not have the trait. So we know that they're, and we're also going to scratch out that. And so what are the chances that Steve is big S, little s? And the answer is 2/3. What are the chances that Karen's big S, little s? The answer is 2/3. Because we ruled out this part. And then, if they do come together in this mating, what are the chances that it's going to be homozygous recessive? And that's 1/4. So there's a 1/4 chance that that would happen. So all of these are independent events. So then we multiply all of these probabilities. We get 2/3 multiply 2/3 that Karen is a carrier, 2/3 that Steve's a carrier, and then 1/4 chance that their kid will have it. If you do the math for this, you're going to get 436, which can be reduced down to 1/9. Okay, the tricky part is this. A lot of people, I bet, did not put that. But we're definitely sure that they're not this homozygous recessive, so you have to assume that they're 2/3 chance, and then you multiply all these probabilities together. Okay. So much for Steve and Karen. Let's move on to the next one. Okay. And the next one is number 18. The pedigree below. Okay, so I'm going to actually draw this pedigree. I'm not going to write down all the names. Tom's over here. Tom marries Sandra. They have kids. They have 2 boys. There's Alan and Daniel. And then Alan meets Tina. And then they have a kid named Christopher. And over here, Anne marries Michael. And then they have a kid, Carla. Now, Carla ends up having it. And Wilma has it. Tom has it, and Arlene has it. Now, the first question is this dominant or recessive? I know right now it's recessive. How do I know it's recessive? These guys right here. They do not show it, but their kid has it. So they have to both be carriers of this trait. Now, I'm going to call this trait. So we big A, little a, big A, little a, and you could go through it, write down this for all these individuals that have it. Okay, and then now to the next part. I know that George up here is also a carrier. How do I know George is a carrier? Because he had to give her one of his alleles. So we know that George is also a carrier. Well, if you do this, this also tells us that Sam is a carrier. And also Anne, we already know she's a carrier. How do I know that? Because if you do the Punnett square of the parents, they're either going to be carriers or they're going to have it. Now, here's the tricky part. We don't really know we don't really know. Let me look here. Here's my thing. What this person is, but we know they have at least, but we're not sure if it's dominant or recessive. Okay. I do know that this one is a carrier, and I also know that this one is a carrier. How do I know they're carriers? Because this guy's throwing out in his sperm, there's a little A in every single one, and they came together for this. So I know that that's a carrier, and this one I'm not sure. We do not know, and we do not know what Christopher is down here. Okay, so this should be how to figure that out. Okay, next one, I think it's the last one. Last one. Okay. Number 19. Your genetic counselor, Charles. Let's talk about Charles' cystic fibrosis. You should know that cystic fibrosis is a recessive trait. Because C's get confusing, I'm just going to draw it this. Or let's do a little f equals cystic. Okay. Now, Charles was married once before, so let's draw Charles right in the middle. He was married once before, and he and his first wife had a child with cystic fibrosis. So we'll say that when he was married, okay, they had a kid, and the kid, let's say it's a boy, had cystic fibrosis. So little f, little f. Well, right then, I can automatically know that, well, hold on, let's read more detail. Okay, the brother of his current wife, Elaine, so this is Elaine. Okay, now she has a brother, died of cystic fibrosis. Oh. Okay. Okay. So let's figure something out here. Let's see, what is the probability that Charles and Elaine will have a baby with cystic fibrosis? Neither Charles, Elaine, nor their parents have it. Okay. So we know that Elaine's family have to be carriers. Why do I know their parents have to be carriers? It's because the only way they can have a kid with it is if they both have that trait. Again, you get one from mom, one from dad. So Elaine could be any one of these. So let's figure out Elaine. Elaine could be this. Elaine could be this. Elaine could be this. But we know she is not this. So now, what are the chances that she is a carrier? Is 2/3. Okay? 2/3. 2 out of 3. 1, 2 out of 3. We don't know for sure. But Charles, on the other hand, we know Charles is a carrier. Okay? Now, if they have a kid, we could do the math, or you could do a Punnett square. We know that if they have a kid, it's a 1/4 chance that the kid will have cystic fibrosis. You can do a Punnett square for their mating. So how do you figure this out? You basically take the probability that Elaine is a carrier, which is 2/3, multiply it by the chance that if they came together, they would have the kid. 2/3 times 1/4, you're going to get 2/12 or 1/6. And that is the answer. Okay, and that wraps up all our questions. You're welcome to practice more of these to make sure you know it. If you can do all these genetic problems on these pages, you're going to do fine on this part of the test. All right, thanks.